Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex, and today is May 10th, 2025. We're looking at an ICLR conference paper, Language Representations Can Be What Recommenders Need, Findings and Potentials, published just over 3 months ago, on January 22nd. This paper explores if language models, or LMs, which are AIs trained on vast amounts of text, already understand user preferences. It asks if their language representation space, that's how these models internally organize language information, also holds collaborative signals, which is basically info on what similar users like, for better recommendations. So to test this, Figure 1 really lays out their initial experiment. Part A shows taking an item's title, getting its language representation, and then using linear mapping, a simple mathematical projection, to move it into a behavior space, where items are grouped by user preference. Part B is a bar chart, showing this linear mapping outperforms standard recommenders on metrics like recall at 2.0. Basically, how many good items are in the top 20 suggestions. Then, Part C uses a visualization technique called TSNE, which helps picture complex data in 2D to show this mapping in action, grouping similar movies. This strongly suggests the language model's understanding is directly useful for recommendations. Building on that initial finding, Figure 2 then digs deeper into how the language model's size impacts performance. We see 3 line graphs for movie and TV, games, and books. And in each, as the language model size grows from 7 billion parameters to 13 billion, then 70 billion. The recommendation quality, using recall at 2.0 and another metric, normalized discounted cumulative gain at 20, or NDCG at 2.0, generally improves. Normalized discounted cumulative gain at 20 also assesses the top 20, but it really values getting the best items ranked higher. So bigger language models are proving more effective. Okay, so following on from how language model size helps, Table 1 here really drives the point home. It compares that linear mapping technique, using various language models, against classical ID-based collaborative filtering baselines. These traditional recommenders usually work with unique item identifiers. Across datasets like movies and TV, video games and books, and using metrics like recall, normalized discounted cumulative gain, and hit rate, which is just whether at least one good item was recommended. The advanced language models like Llama 2 to 7b and text embeddings 3 large often come out on top. This really shows their strength. Alright, so after seeing how well these language models perform, Table 2 then investigates, well, how robust are these language representations? It compares recommendation quality using those familiar metrics. Recall, normalized discounted cumulative gain, and hit rate for item titles alone versus titles with some random noise deliberately added. Across movies and TV, video games, and books, the performance drops only slightly with the noise. This suggests the language model's ability to extract useful signals is quite resilient, not easily disrupted by minor variations in the input text, which is a really practical advantage. So, building on that robustness, Table 3 now directly compares their new model, AlphaRec, against several established ID-based collaborative filtering baselines. These are traditional methods that recommend items by finding patterns in what similar users have liked, typically based on unique item identifiers rather than the item's content. Across the movies and TV, video games, and books datasets, AlphaRec, which relies solely on language, consistently achieves the best scores for recall, normalized discounted cumulative gain, and hit rate. The bottom row even shows these improvements over the best previous baseline are quite substantial. Following AlphaRec's strong showing, Figure 3 examines its design and efficiency. Part A is an ablation study on books. This study tests components by removing them, like its multi-layer perceptron and graph convolutional network, specific learning structures, or its contrastive loss training method, which helps it learn by comparing items. It confirms these are all vital for AlphaRec's top recall and normalized discounted cumulative gain. Part B then shows AlphaRec trains much faster, needing fewer epochs, or full training passes, to converge, reaching peak performance quicker than other models. This rapid convergence is a key advantage. So to wrap things up, this research really shifts our perspective. It shows that advanced language models aren't just about understanding text, They also capture complex user preferences and collaborative signals, which are patterns of how groups of users interact with items. This means models like AlphaRec, built purely on language, can outperform traditional methods, train faster, and even make good recommendations for totally new items, a capability called zero-shot recommendation. It's a fascinating link between language and behavior. That's all for this AI Research Roundup. Thanks for tuning in.